Hey guys, today we're going to be looking at some more complex circuits in great detail. We're not going to have any new concepts, but we're going to look at the process of how to actually solve all of these circuits for current and voltage and power and all of those things using the rules we've already learned. So before we actually look at the circuits, let's look at the two different strategies we could use. There are two options. The first option is based off of Ohm's law, V equals IR, and using equivalent resistance or total resistance of a circuit. So that was what we looked at on the first day with like parallel circuits and series circuits. Those are going to be this first method. And then the other method we could use is Kirchhoff's laws, which is the loop rule and the junction rule. So there are different scenarios when you'd want to use one or the other for solving a circuit, and there are some where you could use whichever you're more comfortable with. Ohm's law and equivalent resistance usually works best when you're dealing with a lot of resistors and only one battery or only one voltage source. Kirchhoff's laws are better when you've got multiple voltage sources and mixed components, which means you could have some resistors, some capacitors. We actually haven't looked at capacitors yet, so we're not going to be dealing with those today. But if there's a capacitor, you're going to end up wanting to use Kirchhoff's laws. To start off with, we're going to look at this circuit. We're going to solve for voltage, current, and resistance for each of the resistors. And we're going to try using both methods. One will use Ohm's law and series and parallel circuits. The other one will use Kirchhoff's rules. So let's start off doing Ohm's law and resistance over here. And the key to working these circuits with either method is staying organized. That is the key. The way you work problems with Ohm's law and an equivalent resistance is you take all of the resistors and you basically combine them into one resistor. In order to do that, you have to know if things are in parallel or in series. It's pretty easy to tell here that these two are in parallel and this one is in series, but sometimes it gets more complex than that. So I'm going to show you my method again of how you do this with a quote line diagram. When I say quote, I mean I made that term up. That is the term I use. It is not probably one you'll find elsewhere. So just know that when you get to college, if you show your professor this and you call it a line diagram, they probably don't know what it means because I made it up. To draw that diagram, you start off on the the positive terminal of your battery, which is going to be on this side, the side with the long line. So we start off on that side with positive 10 volts, and we're going to draw the circuit in line form, starting at that one positive terminal. We go around the circuit, and the first thing we come across is a junction. So after going a little bit in a wire, come to a junction where we're going to split the current into two separate branches. One branch goes down through a 10 ohm resistor. I'm going to draw that right here. It's a 10 ohm resistor. And the other one travels through another 10 ohm resistor. That's going to be my other branch down here. Obviously, those are in parallel. They join back up at this point, which is a junction right there. Join back up, join together, and continue on, coming across a 5 ohm resistor before ending up at the negative terminal of the battery, where voltage equals 0. And that's the whole circuit in line form. Now, a bookkeeping thing that you should do when you work these problems is label each resistor with a number. So I'm going to call this resistor 1, this resistor 2, and this down here resistor 3. So we're going to find the voltage and current in each of those resistors. Some people like to construct a table, which I think is a very intelligent thing to do, but a lot of times I just end up not being that organized. We'll do one here set a good example. We're going to find, or we already know the resistance. We're going to find the voltage and the current for each of these things. So I'm going to switch those, though. I'm going to do current first and voltage last, because I know I can multiply the current and the resistance to get voltage. I'm going to find those three things, and then also I want to find power, just for funsies today. I'm going to find each of those things for resistor 1, resistor 2, and resistor 3. To evaluate this, we first start by taking this big circuit over here, this thing, and we're going to condense it down. We're going to take all those resistors and come up with their equivalent resistances. To do that, we're going to work with series and parallel circuits. You see that right here, I'm going to highlight this new part in red. Oh, that's not a highlighter. There we go. This is a parallel component, parallel circuit. Two resistors in parallel. They are parallel to each other. And you can find the resistance, or the total resistance, of two parallel things with the equation 1 over R parallel equals the sum over I of the reciprocal of the resistors, because it's in parallel. Here that's equal to 1 over, let's see, this is R1, this is R2. 1 over R1 plus 1 over R2. Each one is 10, so that's 1/10 plus 1/10 equals 2/10. Take the reciprocal of that to get RP, and you have the resistance of that parallel part equals 5 ohms for the red highlighted bit only. I'm going to highlight that as red. Now what I'm going to do is redraw that line circuit, but instead of the entire parallel part, I'm just going to put one 5 ohm resistor. And then the second 5 ohm resistor that we come across. So this is 5 ohms. It came from that red circuit. And the other one is 5 ohms. Now I'm going to take those two things in conjunction with each other. They are currently in series. To find resistance of something that's in series, you just add the two things up. So our new circuit that's made up of one resistor, which is just the equivalent resistance, looks like this, with these two things added together to get 10 ohms. So overall, this whole circuit has a resistance of 10 ohms. We can use Ohm's law with that to calculate the total current of the circuit. So down here, I'm going to put our total, just so we know. Our total is 10 ohms. The current total for the whole circuit is found using Ohm's law, V equals IR. We know that the total voltage of the circuit is 10, because that's all of the potential we have from the battery. 10 volts. And V equals IR, so we'd have to do V divided by R to get I. I is 1 amps, because it's 10 divided by 10. And if you want to calculate power, power is current times voltage, which here is just 10. 1 times 10 is 10, and that's measured in watts. So that is for the whole circuit. I'm going to highlight it in blue. This is the whole circuit, calculated right there. Now, if we want to find individual resistors, we've got to work backwards from our total resistance that we found at the end. So now at the end, this had a current of 1 and a voltage across it of 12. Sorry, not 12, it was 10. Voltage across of 10. That's for this whole bottom circuit here. Now, if we move up a level to this combined parallel part and resistor 3, we know that since they are in series, current stays the same. Current's the same all throughout this equivalent circuit that we have here. So in this 5 ohm resistor, which is resistor 3, that current has to be 1. Resistor 3, the current is 1 amp. And we know resistor 3 also has a resistance of 5 ohms. Using those two numbers, we can find the voltage. V equals IR. So voltage here across that resistor has to equal 5 volts. And the power is I times V. 1 times 5 is 5 watts. Now we've got to figure out that parallel circuit. We know that this resistor right here was 5 ohms. That's the equivalent resistance of the whole parallel part of the circuit. And it had a current through it of 1 ohm. So the voltage across that whole parallel part is 1 times 5, which is 5 volts for that whole equivalent resistance. Which means the potential between these 2 points on the circuit up here is also 5 volts. In a parallel circuit, voltage across each branch is the same as the voltage across the whole thing. So resistor 1 and resistor 2 both have voltages of, let's see, we calculated it as 5. The voltage across each of those branches is 5 for resistors 1 and 2. So we can fill that in the chart. Resistor 1 has a voltage of 5. Resistor 2 has a voltage of 5. And they each have a resistance of 10 ohms. You can calculate current from that using Ohm's law. V equals IR, so I equals V divided by R. 5 divided by 10 is 1/2. 5 divided by 10 again is still 1/2. So resistors 1 and 2 have that current split in half between them, which makes sense. You got 1 amp of current flowing around to begin with, and there's 2 paths. Each one is the same. They're identical, so the current gets split in half. That makes total sense. Last thing to do, calculate power from those. You take I equals 1/2 times 5, you get 2.5 watts. Same with the next one, 1/2 times 5 is 2.5 watts. Something that we haven't really talked about a whole lot is that the power through all the components, which is right here, adds up to the power of the whole circuit. This is always going to happen. All right, now what we're going to do is evaluate this whole circuit again, but using Kirchhoff's rules instead. This time around, we're using Kirchhoff's laws, which are the loop law or loop rule and the junction rule. I guess most of the time they're called Kirchhoff's rules and not Kirchhoff's laws. Really doesn't matter though. We got the junction rule and the loop rule. So the way that you analyze a circuit using Kirchhoff's rules is you have to write a system of equations for a bunch of currents. And the steps for doing that are as follows. First thing you do is you find all of the junctions in your circuit. I've got a junction there, junction there. And every route possible between junctions, there has to be a current. So we're going to draw those currents. I'm going to make them different colors so we can differentiate between the currents. First current I see is going to be this one going around to the right between the two things. So there's a current there. We're going to call that current I1. We don't know what it is yet. We're finding it. Now the weird thing about Kirchhoff's rules is that you have to arbitrarily pick a direction you think that current is going to go. It does not really matter which direction you choose. If you choose wrong, in the end, you'll get a negative answer for I, so you'll know it's just supposed to be going the other way. I'm going to make mine point this direction, which would be like clockwise if you're talking about going around the loop. But you have to take a direction. You have to define it as a specific direction, otherwise this whole thing doesn't work. My next current I'm going to choose is going this way between those 2 points along the middle path. I'm going to call that one I2. And the last one goes around the left side of the loop through this resistor and through the battery. I'm going to choose it. Well, I was choosing it the correct way. I'm going to choose it the wrong way this time. so that it goes like this. So you can see what you're supposed to do when it goes the wrong way. All right, so the way that you would work a question with Kirchhoff's laws or Kirchhoff's rules is you use the junction and the loop rules to figure out a system of equations. We're going to start with the junction rule. There are two junctions here that we are going to look at. The junction rule says that current going into a junction has to equal current going out of a junction, which makes sense due to conservation of current. So let's look at this top junction. There are three currents. They are all going out away from the junction, which is weird. But it'll mathematically work itself out. You should know intuitively that that's not possible because there's not a source of charge there. So one of those currents has to be flowing in. What we're going to see is that one of those currents will end up being negative, which means it's going backwards from the way that we drew it. So one of those currents is going to end up going in. But the way we drew it, we don't have any current going in. Sorry, I'm yawning because it's late. So that side's 0. The current going out is the sum of all of those other currents, I1, I2, and I3. They're all going out. I1 plus I2 plus I3 equals 0. Current in equals current out. Now you could evaluate the other junction, but if you look at it and think about it, you see the current going in is I1 plus I2 plus I3, and the current going out is 0. So that would just give you the same equation you already have, which is kind of mathematically redundant and pointless, and so I'm not going to write it down. All right, after the junction rule, there is the loop rule. The loop rule says that the potential difference around a loop equals 0. So what we're going to do here is pick two loops to evaluate, and those are going to be like the two boxes. When you choose to evaluate loops, you pick a direction that you want to evaluate the loop, not the direction you think current is going through the loop, the way that you want to evaluate it. I'm going to evaluate both of these going clockwise. This one's going to be loop 1, going clockwise. Second one is going to be over here, going clockwise. So loop number 1 is going to start somewhere arbitrarily. We can decide where we want to start. I'm going to start at the negative terminal of the battery, right here. And to evaluate the loop law, you start at whatever point you've chosen. It does not matter what point. You could choose literally anywhere. You're going to start at that point and go around the circuit in the direction that you predetermined when you drew your little arrow. So this arrow guy right here, I drew it going clockwise, so I'm going to evaluate the loop going clockwise, even though my currents that I drew may not necessarily go that direction. So if I move through the battery, going from the negative terminal to the positive terminal, potential increases according to the voltage of the battery. So to start with, going from the point I'm at to the other side of the battery, you gain a potential of 10. I'm going to leave off the unit just for simplicity's sake. And then you continue going around the loop. There's just wire here. Wire doesn't do anything. Get to the junction, and we go down into the resistor. Now, across this resistor, we're going to lose some potential because we're moving the same direction as current. As current goes through a resistor, it loses potential. We're moving the same direction as the current, so we're also losing potential. The potential drop across a resistor is equal to IR, V equals IR, Ohm's law. We don't actually know what I is, so we say that we're losing potential, which makes it negative, and that potential is I times R. R is 10, I here is I times 2, because that resistor has current 2 going through it. As you continue along the loop, after you go through that resistor, you get to a 5 ohm resistor. Now, if you look at the current we drew, we're going through this resistor against the current that we drew. If we're going against the current in a resistor, we're going from the low potential end to the high potential end. So we're actually going to gain some potential there. So that potential is IR, V equals IR. So you add 5 ohms times the current there, which is I3. And then as you continue around the wire, you're back to the point you started at. And the whole voltage around the loop has to add up to 0 because you're starting and ending at the same point, so you can't have a potential difference. We're going to do the same thing for the other loop, loop number 2. Start at an arbitrary point. I'm going to start at this bottom junction right here and move around clockwise. As I move up this first section, I get to a resistor, and we're going backwards from current in the resistor. So we're not gaining energy itself, not actually, but we're moving mentally from the point of low potential to a point of high potential, which means we're gaining a certain amount of potential. That potential is given by Ohm's law, I times R. I there is I2, R is 10, so it's I2 times 10. And then we're at the other junction where nothing happens, moving around through the wire where nothing happens, down to this 10 ohm resistor. We are moving through this resistor the same way current is, so we are subtracting potential. The potential we're subtracting is I times R. Current is I1 in that section times R, a resistance of 10. And keep moving around the circuit, get back to the same point we started at, so the total must be 0. And now we have 3 different equations to use for solving for these currents. We've got this top one from the junction, and we've got 2 from the loops. And we're only looking for 3 different currents, I1, I2, and I3. So 3 equations is sufficient. You need the same number of equations as you have variables in order to solve a system of equation. So we've got 3 equations and 3 variables, I1, I2, and I3. So we're all set. We get to solve these. What you can see is that from equation number 2, I2 times 10 equals I1 times 10, which means I1 equals I2. Awesome. So what I'm going to do is everywhere there's an I2, I'm just going to replace it with I1. This equation becomes 0 equals I1 plus I1 plus I3, which is 2I1 plus I3. This one right here becomes 10 minus 10 I1. I'll write it over here. 10 minus 10 I1 plus 5 I3 equals 0. And from this equation, we have 2I1 plus I3 equals 0. And we can do some elimination here. If we multiply this equation by, let's see, that one right there. If we multiply it by 5, we get 10I1 plus 5I3 equals 0. Combine it with that equation, and you get 10, these two will cancel, plus 10I3 equals 0. And for I3, you get -1. That -1 simply means that we chose I3 going in the wrong direction. I3 should be going opposite of the blue arrows, but we still know the current. So I1 and I2 are equal. I3 is -1. You can use that to figure out what I1 and I2 are. That would say I1 plus I2 minus 1 equals 0. I1 plus I2 equals 0. You know that they're equal, so each one has to be a half. Sorry, I went too fast there. That means I1 plus I2 equals 1, which makes each thing a half. So So now that you know all of the currents, I1, I2, and I3, you can calculate voltage across each resistor and power with I times V. And you can go back and check and see that this should be and is consistent with the previous method. So the takeaway here is that this circuit could be solved using either Ohm's law and equivalent resistance or Kirchhoff's laws. Which is easier? Well, I think if you're solving the systems by hand, it's going to be the other method with Ohm's law. But if you really like systems, or you know how to use matrices to solve systems, Kirchhoff's laws or Kirchhoff's rules could be a really good way to solve this. It just depends on you and your personal preferences. Either one would work for this circuit. This one we're not actually going to work out. It is the same example as I used the other day in class, where we found the equivalent resistance of this whole thing. So if you want to see how to do it with Ohm's law, go back and watch that video and it'll show you how to do it. If we were going to do this with Kirchhoff's laws, we would start by drawing points at each of the junctions and drawing current between all of those junctions. So we'll start off with a current between this junction and this junction. We got one going this way, or I choose for it to go this way. It could go the other way if you wanted to. Call that I1. Current going between those two junctions through the middle, I2. Current going through these two junctions, I3. Another one down here, I4. Another one right here, I5. And yet another one around this way, I6. Note that I just chose these directions at random. They're not necessarily the way current goes. If I picked backwards, then we'll end up with a negative current, which just means the arrow flips. Easy peasy. So the deal with this is we're going to have to solve equations for 6 variables. This is going to be a 6 variable system of equations, which sometimes works out easily, sometimes it doesn't. If you're very good at systems or know how to compute them with matrices, Kirchhoff's law would be a great way to do this, because you're not going to have to write out that equivalent resistance thing a bunch of times. However, if you aren't good at systems and you're bad at matrices, don't know how those work with systems, have zero idea what I'm talking about there, then solving a 6 variable system is going to be really, really difficult. So I would recommend doing it with Ohm's law. Again, you can do either of these things. It is valid, but you really need to just evaluate your mathematical skills and your skills at breaking down the circuit and see which is a better method for you. All right, this example is one of multiple batteries. You've got a battery here, battery there, battery there. With circuits that have multiple voltages, multiple sources of potential difference, you cannot use Ohm's law and equivalent resistance, because batteries don't really fit into that method in the middle of it. You can just have a potential difference that you know over the entire thing. If you've got multiple potential differences, that's a whole other story. You can't do it. There's kind of a back way weird tricky method that you could try. I'm not going to show it to you because it's confusing unless you really, really know what you're doing. So things with multiple batteries, we're going to evaluate using Kirchhoff's laws, because that'll end up being way easier. So the first thing you do with Kirchhoff's laws is draw your junction points, label some currents. I'm going to actually make my currents different colors here, help us out. Here in the middle, we're going to have I1 going around this left side, and have I2, sorry, that was the right side, and then going around the left side, I'll have I3. Again, these directions are arbitrarily drawn. You could draw them whichever direction you prefer, but that's the way I'm drawing mine. If I get it wrong, then I'll get a negative current and I'll know the arrows should be switched. So the way to evaluate with Kirchhoff's laws is starting with the junction rule, which is current in equals current out. And we just choose a junction to look at. The current into this top junction is only I3. I3 is the only one going in. And the current out of the junction is I1 plus I2, because those are the two currents that we have running out of the junction. Cool. That's one equation we can use for our system. We're solving for 3 currents, so we need 3 equations. That's one of them. If you look down here at the other junction, it's mathematically equivalent to this first junction. You'd have I1 plus I2 going in equals I3 going out. Mathematically equivalent to this first one, gives us no new information, so we can't use it in our system of equations. Next up is Kirchhoff's loop rule. So we're going to take each side of the circuit and evaluate it as a loop. I like to go clockwise. You can go whichever direction you'd like, but I like to go clockwise. And you choose arbitrarily a point to start at. I'm going to start at the positive terminal of the left side battery on the left side loop, and I'm going to evaluate the left side loop. I go around that loop counterclockwise, or sorry, not counterclockwise, clockwise, like my little swirly here thing indicates, because I picked that direction. Now, as I move along this circuit, I'm going to get to an 8-volt battery. As I move through this 8-volt battery, I'm going against the battery, which means I am losing potential through the battery. I'm going backwards through it, essentially. So what I will write down is a negative 8 volts. And actually, I'm just going to leave off the volts for now. I know that's bad form, but I'm going to do it. And then I'll keep going through the circuit. Down to this junction point, going left, because I'm on the left side loop, go through this little resistor. There is a voltage drop across the resistor because we're going with the current. We're going forwards through the resistor. That voltage drop is equal to I times R, which is Ohm's law. I is I3 times the resistance, which is 2. So we need 2I3, and that's subtracted because I'm going forwards across the resistor, and you lose potential across the resistor, getting all the way to the negative terminal of the battery. At the negative terminal of the battery, I move from negative to the positive terminal. Over that area, I gain 2 volts. So I put plus 2 volts. And the loop law says all of that voltage added together should equal 0. Now we do the same thing for the other loop. Sorry, this is another equation I can use in the system. This is an equation. We're going to find that last equation using the other loop. So this loop, I want to start, it doesn't matter where, I'm going to start at the negative terminal of the 9-volt battery, right there. Follow the circuit around. As I'm going around the circuit, I get to a resistor. I'm going forwards through that resistor because I'm going with the current. So that one is going to subtract voltage. The subtracted voltage is equal to I times R. I is I2. R is 1. So just I2. Keep moving through the circuit. We get to the battery. We're going from the low potential to the high potential end of the battery. So we add 8 volts. Sorry, I'm going to leave out the unit. We add 8 volts of potential as we go across that battery. Then keep going around the circuit. You end up at the positive terminal of the 9-volt battery. You go across it to the negative terminal. As you go from a high terminal to a low terminal, you're losing potential. So we're going to subtract 9 volts there. And then we've reached the place where we started. So that total loop has to equal 0 on the potential. And those are our 3 equations that we're going to use. Now we just have to solve these for I1, I2, and I3, which ends up being super easy. You can solve for I2 directly from this equation. Negative I2 equals negative 1. Therefore, I2 equals 1. And we found I2. Likewise, you can solve this one for I3 all by itself. You get negative 8 plus 2 is negative 6 minus 2I3 equals 0. So I3 equals 3. Sorry, I3 equals negative 3. So we had I3 going backwards from the way it should be. It's actually going around that circuit counterclockwise. And then we use this equation up top with our values for I2 and I3 to determine I1. I3 is negative 3 equals I1, which we're looking for, plus I2, plus 1. Therefore, I1 equals -4, which means we got I1 backwards as well. It's just flipped from the opposite way. To determine voltage across these resistors and also power, you'd use these currents combined with the resistance. Resistor with 2 ohms has current of I3, so it'd be 3 times 2 is a voltage drop of 6. Do the same thing with the 1 ohm resistor. 1 times its current, which is 1, gives you voltage drop of 1. From those things, you can figure out the power, etc. So using Kirchhoff's laws here and solving that system really wasn't super bad. I'm going to leave this last problem as an exercise for you guys to do. You can try it on your own if you like. This one's going to be more complex than you'll see in AP. You will not have to evaluate something like this for the AP test. It's just something I think is fun to do. I enjoy doing. It's a good puzzle kind of thing. It does have a 6-variable system, but that system is not super hard to evaluate. So if you try it, you should be able to evaluate for all of those variables pretty easily without any without any elimination processes in your algebra. So try this one if you'd like to. You do have to use Kirchhoff's laws because there are 3 batteries. You cannot use equivalent resistance. Don't try it. It won't work. Hopefully you kind of understand a little bit better how to work these circuits. It's not something that you'll be tested on super in depth, but I think it's fun and interesting, and it shows you how these rules apply and how to use them. Hopefully you enjoyed this lecture. Sorry I'm getting it to you a little bit late. It's not going to help with your homework too much because there's not a whole lot of solving these things in your homework. Make sure you're doing your homework by Monday. It's in the online portal. On Monday we'll have a review for tests. There will be a test Tuesday. I might maybe push that to Wednesday, depending on how the rest of this week goes. But plan for test on Tuesday, and hopefully you enjoy doing these circuits and you have fun with this last problem.